Alright class, as we're wrapping up the end of this semester, we're going to revisit some old topics and make sure you guys have some understanding of important things like stack cookies and exactly how they work and exactly the techniques that are used to bypass them. And then cover things like SSL and all the bugs and what they mean for web application security, internet security, and for the internet as a whole, because the latest heartbleed bug could not have come at a better time. Then we're going to cover certificate authorities and the trends in signed malware, and then revisit the big picture and talk a little bit about the exam next week. So earlier in the semester, when we covered stack cookies, we explained how the stack works and where they are on the stack. And this is cut and paste from this FRAC article, which we're going to dive into just a little bit, and explain how there's local variables and there's this canary or stack cookie that protects the return address. And so let's dive into exactly how that happens. So there are many implementations of canaries, stack cookies, and it is mainly a compiler mechanism. This adds in code to the epilogue of each function, code to the initialization of the entire process, and that they do setting up the stack cookie, which is at the initialization time of the process, so it chooses a random integer, and then at the epilogue of each function it checks that it's still there and hasn't been corrupted on the stack. So the most important one to know about is one that was originally called ProPolice, but is now called Stack Smashing Protector. And it's been in GCC since version 4. And so exactly how GCC works is that in addition to the canary, there's usually some sort of form of padding. And the stack grows downwards in this diagram. And so however many functions away this is, and then the previous function, and then this is the current function with the local variables, and dot 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 is basically unused space in the memory segment for the stack to grow into. So at the base of where all the local variables grow into the stack, the canary is placed, and then there's some padding. Padding can be used for alignment, this and that, but it also mainly prevents, on top of the canary protection, because these things are implemented in a modular fashion, not relying on each other. The padding prevents off by one errors from writing 1 byte of maybe the frame pointer or the return address from a vulnerable function that writes to a location here on the stack. Now, so in addition to the padding and the canary, if you want to buffer overflow upwards and overwrite the return address, once return is called, it's going to have to get past the epilogue code that checks the state of this canary on the stack to make sure it hasn't been corrupted. And in order to get past that, you have to overwrite this with exactly what the canary is. Now, it's impossible to know remotely, and in local privilege escalation, it should be impossible as well, because you're not going to have access to read the memory segment that the canary is stored in if the process you're exploiting is a higher privilege process. Hence, the point of privilege escalation. If you're trying to exploit something that you have already privileges to, there's no point. What is the point? So there is a way to get around this, and we covered arbitrary writes, in which you basically tell it the address in memory to write a provided value. And so the way that this may manifest is two vulnerable memory writes back to back, or in some fashion in a function. And what happens is this first memory copy puts the argument into buff. Buff is here. And let's look at what this looks like on the stack. So buff is going to write upwards towards higher memory, and the stack grows down towards lower memory. And it writes and writes and writes, and doesn't properly check the bounds. It instead passes at the string length of the source, not the destination. So that's vulnerability number one. But this allows you to write this way. So you still have actually the ability to overwrite pointer. So stir copy here is destination source, and again overwrites writes with whatever is provided to the function at the destination pointed to by PTR. If we can change PTR, we can tell it to write somewhere else. So we can tell it, if we know the address of the return address on the stack, to write here, and the first integer or first 4 bytes of the argument are going to be used for the return address in the 32-bit system. And this is a way to get around the canary in this stack frame to exploit it. Now you can't always rely on 2 vulnerabilities to exist in the same function to exploit it. And indeed, this is a good mitigation, because in cases like this, it doubles the cost or doubles the price of exploitation. It makes it so you have to find 2, not just 1 vulnerability, and they have to work just like this. However, we still haven't really talked about how to efficiently brute force canaries. And it turns out it's way easier to deal with remote target processes in brute forcing canaries, as opposed to doing it in local privilege escalation. And it works out like this. When developers design a program to accept new connections and then fork off and handle them, there's one of 2 ways it typically happens. Typically, it just happens to fork and the child reads from the socket and handles the connection. Occasionally, a security-minded developer knows the benefits of execve and can get away with doing it, and it doesn't incur too much of a performance overhead of spinning up an entirely new process. Now, what happens when fork is called, it creates a copy of the given process, and the parent and child start executing. The child has exactly the same stack, exactly the same heap, doesn't share the stack or the heap necessarily, and the implementation can vary across operating systems here. However, any variables, local variables, and any stack canaries will still be the same in the child. Now, what happens is this allows you to brute force, remotely brute force stack cookies and other defenses, exploit mitigations, I should rather say, in settings like this, where there is not execve or execv being used. Now, when execve or execv or whatever is being used, this creates a new process space and reinitializes the whole process. So ASLR is initialized again, dep is initialized again, in case it's been somehow damaged or tampered with thus far. Stack cookies are rechosen, it's reinitialized, and everything else. And then the process goes about doing whatever the given code dictates. Now, in this avenue, this allows you to keep trying guesses at a target's stack canary when there's no execve, without the canary being reset after each try. And you can crash it each time. Seg fault caused by your buffer overflow smashing the stack, and it's still going to keep accepting connections and forking off children to allow you to keep exploiting. Now, on 32-bit systems, there's approximately, where is it in here? There's approximately 4 billion different stack cookies that could be chosen. Obviously, many, many more for 64-bit systems. Now, that is somewhat infeasible to approach brute forcing, but there are differential timing analysis attacks that you can use to brute force smartly. And we'll explore that. So the idea is that if you do an arbitrary write of just one byte against the stack canary. Say this is the stack canary. And C here is the canary, and it's an integer, it's a 32-bit system, so it's 4 bytes here. What you would try is you would just write your buffer overflow, however many padding you need, or whatever you need to overwrite to get past all the local arguments to actually get into the canary space, and then just write 1 byte. And start at 00, then 01, 02, 03, etc., etc. The goal is that if you guess wrong, the stack canary is going to get corrupted, and it's going to sig abort. But if you guess right, it's going to continue execution as normal. So it gives you a tell on how close you're getting, and you can use this like a safe cracking approach to hear that click when you get one number in the combination right. So what you do is, say for instance, you would target the first byte and you keep guessing, you get all the way to capital X and it succeeds. Well, then you don't have to try any more of those bytes. So you trim out the rest of the state space that you have to test, and you move on to the second byte. And so you keep going, keep going, keep going, and capital Y is the next byte. And rinse repeat, and then capital Z is the next byte, and then capital A is the next byte. And when the attack is finished, you'll have guessed all the bytes of the canary, and you're not crashing the program anymore. Then you can go on to overwrite the return address and land an exploit and deliver a payload, and then tie it together in an overall exploit. So that is the main message I wanted to get across about brute forcing stack cookies and how that works in practice. So things to keep in mind from a defense's perspective is that if you can afford the performance overhead, if you design your programs when they fork to handle new connections to exec VE the code that is used to handle the connection, you mitigate this entire avenue of attacks and also the avenues of brute forcing ASLR. Because after you're done brute forcing the canary, when ASLR and DEP are enabled, in order to land your ROP chain without having an info leak, you have to brute force ASLR. And while the cookie may take some time to brute force, then the next step of brute forcing ASLR is in effect. However, if you have it exec VE every single time, it makes this avenue of attack completely infeasible. Which brings us back to the rest of the lecture. Skip forward here a little bit. And we're revisiting this. By exec VEing, you kick off the reinitialization of ASLR. The code is put in the initialization segments of the .text segment of the binary and other things. So for the final, I'm not going to have any exploitation exercises that you have to turn in shellcode or anything like that. But overall for the class, you should know for the generic stack buffer overflow, how to exploit it, and then when you add stack cookies, how you exploit it still, under what conditions it might be easier. Obviously, we just covered that doing it remotely and when it just forks without exec VE, it makes it actually exceptionally easy to detect whether or not you're guessing the cookie right. Then what you need to exploit it and land a payload with DEP, what type of exploitation technique you would need, and then also with ASLR enabled on top of that. And perhaps under these conditions you might require another bug or weakness to pull off the exploit. And then, as always, think about how to further mitigate this cat and mouse game. And then for heap buffer overflows, obviously we covered how the stack cookie works for GCC 4.0 and beyond, but that was very specific to that compiler. And so likewise for heap stuff, heap exploitation techniques, very much depend on the compiler's implementation of heap allocator and the heap free and all the algorithms are used to maintain the free list and do the unlinking. And whether or not cookies on the heap may affect it. There may be cookies between each chunk. There may be cookies protecting the heap metadata, and how similar to the previous example covering just the basic stack, how there might be certain conditions that make it easier to brute force a cookie on the heap. I should just add this to say with metadata cookies. Now think about trying to land an exploit with DEP on, and then also ASLR, and whether or not you might need another bug or weakness, and then think about how to further mitigate and also further exploit attack, defend, attack, defend. Then for integer bugs, which perhaps enable an arbitrary write, say for instance, you control the index of an array write, and it's not properly checked, and you're able to enter like a negative number. So you might be able to write the return address. So how you might do that with stack cookies, obviously you can directly bypass them because you're not overflowing to it, you're just arbitrarily writing them precisely. Now with data execution prevention, then ASLR, etc., and the future of mitigations, you should think about like control flow integrity, the EMET suite, that we haven't covered them that much. I might send out a paper on both. And then similarly, partial arbitrary byte write. So similar to this, say you can only overwrite one byte and off by one error of a pointer, and then write a value at that pointer. So you can control like the upper part of it, what might you target, things like that. Anything that's statically located there might be a good target, especially if it has function pointers. Maybe if it's already pointing in the neighborhood of the global offset table or the PLT or things like that. Now, use after free exploitation, whether or not metadata cookies even mean anything for that, and the circumstances under which DEP might help and might not help mitigate it, and then ASLR, if that affects it. Depends obviously on the nature of the use after free. It is possible to allocate executable code onto the heap or onto a heap, and then execute it. It's under certain special circumstances that happens. It's not a very common thing, but it is possible. Then, as we saw on midterm number 2, the use of uninitialized variables and under the circumstances that those might be able to be exploited. Then also think about how stack cookies might affect it, if at all. DEP, ASLR, and if any other mitigations actually go to help it. Format string bugs, and going on and on. Now, in each of these scenarios, you should consider the two possibilities: exploiting it locally to do local privilege escalation, and then also exploiting it remotely, and remote code execution is the goal. And we've talked about things like signature-based antiviruses are inherently limited in their design, and there are techniques that specifically defeat them, and it's effectively under the realm of polymorphism. And then exploitation through a firewall means going over the accepted channels that are already allowed into the network, and then going through a web application firewall means going through the accepted data formats that are accepted into each input, so exploiting in the ASCII only realm and how encoders affect that. And if you need to land your exploit and say overwrite the return address to point somewhere, what would happen if your address that you overwrite to point to the beginning of your ROP chain or to your NOP sled and shellcode? Well, what happens it's in a region of memory that is not all ASCII characters for each byte of that address. How does a web application firewall mitigate attacks like that? So you have to understand that. Then it brings us to, oops, this should not be getting cut out. One of the most important bugs of all of InfoSec, the Heartbleed bug. And the number of SSL bugs that have come out this year have really been historic. It started off with the Apple go-to-fail bug. Then was the GNU utils bug that did not properly check certs. And finally, the Heartbleed bug, which has its own dedicated website, allows attackers to, given enough tries, read the memory contents of a server, and eventually they can get the private key of the server, which breaks the very principles that are relied on in asymmetric key encryption. The private key is kept private. And this really goes to show that information security is way more than just crypto and assuming your crypto is properly implemented. This bug is the quintessential nail in that coffin. It is only affecting the implementation of OpenSSL. But OpenSSL is used by almost every Linux distro, used by many browsers, used by many web applications. There might be a link or table. Nope. Oh, I have a link back in the lecture. Here we go. So, there is a list that the nice people at Mashable put together on what services are affected. So Facebook was affected, Instagram, Pinterest, Tumblr, Google was affected, Yahoo was affected, Gmail, Yahoo Mail, Amazon Web Services, Etsy, GoDaddy, Flickr, Minecraft, Netflix, SoundCloud, YouTube, etc., etc., etc. Now, the actual list of affected is much larger than this, and you may still be affected if you're not on this list. I'm going to talk about that in a little bit, but I want to get back to talking about these bugs and what they mean for SSL and TLS. Now, they're not necessarily flaws in the crypto algorithms themselves, and they're not necessarily flaws in the X509 certificate standard itself. They're flaws in the implementations of these complex algorithms. In the case of the go-to-fail bug, that was just bad programming, and that I don't know why you would ever use a go-to statement, and especially in a crypto library. That's just inexcusable. And then the GNU bug that failed to properly validate certs allowed most distros to be man-the-middled whenever they're doing package upgrades and getting packages, installing packages, if I recall correctly. And Heartbleed was found by the guys at Codenomicon, and actually a senior engineer and a co-founder of Codenomicon were scheduled to come out next Monday to the class to lecture on advanced fuzzing techniques. But then two of their employees in Finland found the Heartbleed bug, and they've been working with vendors and OpenSSL to help remediate and patch and mitigate any damage caused by this bug. So they've been very busy, and we've rescheduled them to next year. Here's a good comic by XKCD illustrating exactly how it works. It's basically, there's this heartbeat function in OpenSSL that allows a client connected to an OpenSSL server to keep the encrypted tunnel alive. And so there's a function called heartbeat that you send a request to the server to encrypt or sign this little message and send it back to you. But you also specify how many letters you want or how many bytes you want written back to you. So that specification is actually not checked on the server side as to whether or not it has anything to do with the result of the operation or the length of the input you've given it. So the standard use of it would be basically send the server saying, hello, are you there? If so, reply potato and tell me 6 letters. And the server would say potato. And then the same thing, say bird, and the server would say bird. And the way it's exploited is that you just keep sending it very small requests, and it's also in conjunction, if I recall correctly, with an integer bug that allows you to read a very large amount of letters or characters of server memory. So keep doing this, and given the random nature of the heap and how it might look at any given time, eventually you're going to see some sensitive information on there, and you may see what the master key is or the private key that the server is currently using. So that's pretty ridiculous. That's pretty hard, game-changing. And Akamai, if you're familiar with them, are one of the largest content delivery providers in the entire world. They are responsible for hosting and distributing over 30% of all of internet traffic in the world. They basically run things ranging from, if I remember, Google to Amazon. It was founded by some of the guys who invented the internet, and they rolled their own, here customers, Microsoft, Al Jazeera, White House, China, Central Television, many security vendors, and then also many social media sites, many businesses, etc., etc. So Akamai came out and said, don't worry guys, you're safe. We rolled our own custom patch for this bug, like overnight, and you're good to go. And it turned out the patch didn't actually fix the bug. And so they were attacked, and their private key was leaked, and they had to quickly actually, I don't know if they were attacked, but they reissued their keys after it was discovered that they are still vulnerable. And if they were attacked and the attackers got away with it, they had keys that allowed them to expose the encrypted web traffic of over 30% of all the internet. So regardless of whether or not you find yourself being affected by the companies and vendors that are directly on this list, you may still be indirectly affected. Time will only tell. So, getting back to the slides, brings us to a new trend using digital certificates. We're moving away from SSL and TLS and complaining about that and the bugs and stuff like that. We covered the shenanigans at the certificate authority level and covered the ultimate problems with being locked into this trust architecture and having no agility in it whatsoever. Well, the bad guys are overwhelmingly exploiting this more and more. Certificates are effectively, the market is you are buying trust. You pay enough money and you get a cert signing your name. You may also have to pay, for rent on a building. You may have to pay for this and that. You may have to put warm bodies in the office to look legit. If they even bother background checking and stuff like that. Now, McAfee, at this article here, put together an article investigating the trends in malware that is digitally signed. The code is signed by a valid certificate that was purchased or maybe stolen or this or that. And it is shown that since 2011 up till now, just in Q3 of last year, that this trend is skyrocketing. And just in Q3 of 2013, the difference in new malware from Q3 to Q2, that means in addition to everything found thus far, just in Q3, 4 months of last year, 1.5 million pieces of different malware were signed by valid certificates, which, on top of the state of SSL implementations and all the bugs that have been hit by it, then it will be only a matter of time till the Q4 number for this report comes out, and then the Q1 number for 2014 comes out. And this may all come crashing down. Who knows? It may be going down, but as we saw in the certificate authority lectures, there's nothing holding certificate authorities accountable. Nothing whatsoever. So, the big picture, now that we're at the end of the semester, for the entire class is that security is confidentiality, integrity, and availability. That's the classical definition of it. The reason we focus so much on offense is it allows you to bypass these mechanisms or gain access to directly attack them. And so we've covered things from denial of service to replay attacks to focusing on remote code execution. And it should be pretty clear by now how each one of these impacts the system. You should be well equipped to communicate the impact of a given attack and a given style of exploitation, ranging from denial of service to distributed denial of service to simple replay attacks on poorly constructed network protocols to remote code execution exploits that rely on vulnerabilities and bypassing exploit mitigations. And we focused a lot on binaries and application security and exploit mitigations and exploit development. And they are really the hardest subject in this whole big picture. Sure, there is a lot we didn't cover. We didn't cover things like directly traversal. We didn't cover direct objects for referencing or cross-site request forgery or cross-site remote file inclusion, forging tokens. Didn't really cover that much. XML injection. And there's so much else that we didn't cover. But we did cover the zero-day aspect very well. And we covered the big hitters like cross-site scripting and SQL injection. And then also certificates and the problems there, the inherent problems and the way it all works. And really, the reason I focus so much on application security is that is my specialty. And also it has been around and is a bit more mature, understanding-wise on both offense and defense. And it gives me a better ability to teach it all in one big class. Every one of these components of a web architecture and a web service, there are dozens of different variants for what each one could be. The complexity is much higher. The argument of whether or not it's really mature, I don't know. We're starting to call things like Web 2.0. And we're on how many versions of operating systems and browsers and stuff like that now. And it's really just an amalgamation of different technologies to work together to present things in a more streamlined, more featureful fashion. And we'll see how it all plays out. Things like HTML5 allow web servers and also attackers to arbitrarily allocate as much space as they want on your hard drive and fill it with things, which can be very dangerous. Can be used to give you malware or do terrible things to blackmail you for forbidden media and disgusting stuff like child porn. So as this keeps skyrocketing complexity, it may eventually plateau to a point where it can be cogently taught in one streamlined curriculum. But if you come away from this class thinking you're a master at web application security and application hacking, you are gravely mistaken. You're really good at application security and exploit development, however, vulnerability research. Yeah, you're pretty damn good there. So, oh yeah, there's still animations in the slide. So yeah, there's all sorts of different technologies, and each one of those has 0 days in them. And it obviously depends on the architecture of that server and if it's running on a different server behind the firewall and what language it might be, whether or not it's JIT code or something else like that. So that'll be it for today's lecture. It's shorter, and we're winding down the semester, and the rest of the semester isn't really going to have tested material. The next week, we're going to have a social engineering lecture, and then try to have a in-class meeting on the last Wednesday, so next Wednesday, a week from today, and we'll be going over physical security and try to get locks and lock picks for people to play around with. And next week, I'll be releasing the take-home final. And that's it.